An autoencoder is a particularly interesting type of neural network. Here's the standard view of autoencoders. We have a dataset x1 up to xn. It's an unlabeled dataset. It might be, for example, a collection of pictures, say pictures of mustelids. The training task for the network is to learn to reconstruct the input, and the challenge is that it has to do it via a low-dimensional bottleneck. We want the neural network to learn to somehow collapse all of the richness of the input down into a small number of dimensions, say 4 or 20 or whatever we like, and we want it to be able to reconstruct the image from just that condensed summary. Of course, we shouldn't expect it to get a perfect reconstruction, especially if we only allow it a few dimensions in the bottleneck. The hope is that it will learn to capture the key attributes of the image, the things that, for example, you'd record if you were trying to tell someone about the input. There's a stoat standing upright with its summer coat on a grass background. That's 13 words, far, far fewer bits of data than it takes to encode the original JPEG image, but it's enough to convey what's in the image. If you know the general types of pictures of mustelids that I have in my dataset, then those 13 words should be enough to let you draw a reasonably good approximation. So that's what autoencoders are for. It's interesting to compare them to another standard setup for neural networks, namely generative modeling. Just like in the autoencoder setup, we start with an unlabeled dataset. The goal of generative modeling is to fit a probability model to the data, and the standard sort of model that we've discussed in earlier videos is a latent variable model. In other words, we want to build a neural network such that if we generate some random noise z, called the latent variable, and feed it into the network, it will produce an image. The idea here is that the noise should encode all the free choices about the image. For example, one dimension of noise might be which type of mustelid we want. Do we want a stoat or an otter or a wolverine, and so on. Another might be the colour of the background. Do we want grass or snow or river? It may at first seem crazily overambitious to be able to turn noise into nice-looking images, but when we think about it, that's an entirely reasonable goal. It just needs us to figure out what the meaningful dimensions are in the dataset that we're given. And now this all sounds very close to what we said about the autoencoder. The job of the autoencoder is to discover the meaningful dimensions along which to summarize an input. For example, to take an input and encode it as stoat, upright, summer coat, grass. And the job of a generative model is to take a low-dimensional summary and turn it back into an image. We'll come back to this connection in a moment. First, let's look at some things we can do with autoencoders, assuming that is that we can train them. Here's a concrete example, an autoencoder trained to encode the images from the famous MNIST dataset. Here I've given it a bottleneck of 4 dimensions, and this is a typical result. It encoded the input image into this 4-dimensional vector called the latent representation, and it decodes that particular 4 vector into a slightly blurry but clearly recognizable digit 8. What's astonishing is that this works at all. I didn't give it any guidance about what axes to look for. I didn't tell it, here are 10 digits and they're all made of pen strokes, and some people make thin strokes and others make thick strokes. I didn't tell it any of that, and it was still able to discover a useful representation all by itself. So here are things we can use autoencoders for. We can use them to remove noise from images. If it's got to compress the entire image down to just 4 real numbers, all it can hope to store are the key descriptors like which digit it is and how thick the stroke is and so on. There just isn't space to store extraneous detail. In other words, the encoder has to learn to discard extraneous detail, and that's what gives it the ability to remove noise. Here's another thing we could do. We could pick a random 4 vector, feed it through the decoder, and we see what it produces. In other words, we can use it as a generative model to create new data points that are similar to what's in the dataset. This is a fairly low capacity autoencoder, and I only trained it for a few epochs on a low power laptop, so it's not perfect, but it's still clearly capturing something interesting. Here's another use. Often we want to train a supervised learner, but we don't have much labeled data to train it on. For example, we might want to learn to classify tweets as to whether they're trolls or genuine. We might hire some Amazon Mechanical Turk workers to classify a few thousand, but that costs money, so we've only got a limited amount of labelled data, but we've got a whole fire hose of unlabelled tweets. The idea of semi-supervised learning is that we train an autoencoder on the unlabelled tweets, and it should learn to pick out the key dimensions of a useful representation of the tweet. And then we can train a classifier, taking the low-dimensional representation as its input. This classifier should be much easier to train because all the hard work of extracting signal from a tweet has already been learnt by the encoder, and so we should be able to get decent results even with just a small amount of labelled data. Okay, so it looks like autoencoders are wonderful. They're the answer to all our machine learning dreams. What's the catch? The catch is to do with training. Let's think about how we should train them. Here's the obvious take. We want the autoencoder to learn to reconstruct the input. So let's simply define a loss function, call it L of x tilde x, say, which measures the difference between the original image x and the reconstructed image x tilde. If the autoencoder is doing its job, then x tilde should be close to x, so we can train it by simply minimizing the loss on the training dataset. And of course, we're good, honest machine learning people, so we know we have to set aside a holdout dataset. After we've finished training, we'll measure the reconstruction accuracy on the holdout dataset, and this will ensure the autoencoder hasn't sneakily cheated by memorizing everything in the dataset. This all sounds great, but it's fundamentally flawed. Can you see the flaw? I'll give you a moment. Here's a thought experiment. Let's imagine we've got loads of money and a great big cluster of high-end GPUs, and we want to train a really super-duper autoencoder, so we set up the encoder and decoder to have hundreds of layers and tens of thousands of nodes. And then the autoencoder discovers that it can get a perfect score by simply encoding the pixels of the image into the digits of the latent representation. It takes the top left pixel and stores it in digits 1, 2, 3, takes the next pixel, stores it in digits 4, 5, 6, and so on. If the latent variable z has high enough numerical precision, then this autoencoder will achieve a perfect reconstruction even on the holdout dataset, but it won't have learned anything at all useful. This is just a thought experiment, and of course in practice we don't train neural networks with crazy high numerical precision. But what the thought experiment demonstrates is that the achievements of an autoencoder, if we can achieve them at all, come from an accident of floating point precision, not from conscious design of the training objective or of the evaluation metric. So this concept of training is no good. In our thought experiment, the autoencoder always makes a perfect reconstruction of its input, so it won't succeed at denoising. It doesn't extract useful features of the input, so that's no help for semi-supervised learning. And random generation won't work either. If we just feed it a latent random variable z, then our thought experiment autoencoder will just produce noise, not an interesting output. Okay, so we need to think much harder about how to train an autoencoder. This is a really deep and interesting and challenging question. The right way to train an autoencoder, and the right way to think about what an autoencoder is, was discovered in 2014 by two independent groups of researchers, and you can find their details in the printed notes. You'll not be surprised to learn that the answer is probabilistic modelling. Specifically, it's generative modelling. Let's forget all about encoders for the time being, and just focus on the task of fitting a generative model. This is the setup. Let's consider a latent variable generative model. It takes an input z, which is noise, generated from some standard distribution. Let's say a collection of independent normal random variables, each with mean 0 and variance 1. Another way of writing this is, let z be normal of 0, I subscript d. The choice of d, the dimensionality of the latent space, is up to us as modelers. And let's suppose the noise is fed through a neural network, and let theta be the network's parameters. Next, I'm going to suppose that x is a random variable whose parameters are given by the output of the neural network. For example, let's suppose we're trying to generate e-dimensional data. I could let x be a collection of e-independent normal random variables whose means are given by the output of the neural network f sub theta of z, and whose variances are all equal, they're all rho squared. The thing that's rather tricky here is that I'm defining a generative model with two sources of randomness. There's the randomness that comes from z, and then there's the extra randomness that's stuck on at the end. It turns out, for reasons that I hope will be clearer after we've done all the maths, that we need to have these two sources of randomness in the generative model in order for this training mechanism to work. Okay, so what is the training? Training any probability model is always the same. It's just maximum likelihood estimation. We want to pick the neural network parameters so as to maximize the log likelihood of the dataset. We'll assume that our dataset consists of n independent samples, x1 up to xn. Because they're independent, the log likelihood of the entire dataset is just the sum of the log likelihoods of each of the individual data points. And how do we work out these likelihoods? Well, x is generated from z, and we know the distribution of z, so we can use the law of total probability. The likelihood of xi is the integral over all z of the conditional likelihood of xi given z times the likelihood of z. Or, here's another way of writing exactly the same thing. This is the integral of some function, call it h of z, times the likelihood of z. In other words, it's the expectation over z. And we know how to compute expectations, or at least how to approximate them. We just use Monte Carlo. Take a sample of z values, evaluate the function h that we're interested in, and average our results. But here's another thought. We've just been learning about importance sampling in the last video. The idea of importance sampling is that we can speed up Monte Carlo if we bias our sampling distribution. In other words, invent some distribution z tilde, sample the values zj from that distribution and compute the averages before, but now we need a correction factor to take account of the biased sampling distribution. We know that if we choose the sampling distribution well, we can get more accurate Monte Carlo estimates, i.e. less noise. And we also know from the last video, from general theory about importance sampling, what the perfect sampling distribution is. Its likelihood should be proportional to the numerator here. I won't go into any more of the maths for now. All the rest of the maths, all the derivation of the training objective, that's all in the next video. For now, I just want to leave it at this. The perfect sampling distribution z tilde should be chosen based on xi. You can see that here, the subscript I hiding in the subscript of h. That's the biggest insight into autoencoder thinking, that we want to choose a sampling distribution z tilde, and we want to choose it based on the data point xi, whose likelihood we're trying to compute. Okay, as I said, I'm going to leave all the maths aside for now, and I'm going to jump straight to the conclusion. Here is the answer, here's the setup for a probabilistic autoencoder. There are two configurations of the network, and we ought to have both of them in mind simultaneously. What we're really trying to do is to fit a generative model, like the diagram shown at the top. Something like this. This is the generative model we discussed a moment ago. But the network that we'll actually use for training is a bit different. We have an autoencoder setup with two neural networks. The second network, F, is just the generative model part. It's the first network, G, that's interesting. The job of G is to take an input little x and compute the importance sampling distribution z tilde. Remember, we said that z tilde should be chosen based on the data point x that we're trying to compute. For example, we could let G compute a mean mu and a standard deviation sigma, and then ask for z tilde to be a normal random variable with that mean and variance. Here's a more explicit way of writing it out. We'll write z tilde as mu plus sigma times f, where f is some standard normal random variable. Here it's a collection of d independent normal of 0,1 random variables. It's crucial for what comes next that we have to be able to split z tilde up like this. We have to be able to write it as a function of parameters computed by G and exogenous noise f. Next, the training objective. Here it is, an intimidating looking function. The goal of training is to maximize this. We're maximizing it over the parameters of two neural networks simultaneously, the theta parameters for the decoder network and the phi parameters for the encoder network. Let's have a talk through what goes into this objective function. The first term has an expectation. This is an expectation over the sources of randomness in the model, and the only source of randomness in this equation is f, so this is an expectation over f. We can just take some samples from f, compute the log likelihood and average. Each sample from f, call it f subscript j, gives us a different value for the z tilde. Given a value for z tilde, we just ask what's the distribution that this z tilde implies for x, and that gives us the log likelihood term. The other term also looks intimidating. It's called the KL divergence, short for Kullback-Leibler, and this is how it's defined. It's the expected value of the log of the ratio of two likelihoods. Basically, it's a way to measure the similarity between two distributions. If the z distribution and the z tilde distribution are identical, then the KL term is 0. The less similar the two distributions are, the bigger the KL term. It's actually reasonably easy to get an exact equation for this, at least for simple distributions for z and z tilde, as we'll see shortly. Okay, so that's the general setup. Let's now look at a concrete example and see what all of these terms actually look like in code. Here's our example. It's the classic dataset of MNIST digits. Each image is 28 by 28 pixels, and each pixel is black or white. Actually, there are a tiny number of grayscale pixels, but I'm going to ignore that for now. And here's a generative model that we can use. As always, it's modeler's choice. The model isn't something that we can prove is correct. It's just a model that we're choosing to use to fit this dataset. Someone else might come up with a completely different model. Anyway, this one is my model. I've printed out math style and I've also written out in code. They both say the same thing. The model says, first, generate a random variable z, a collection of d standard normals. D is modeler's choice. Next, let there be a neural network f, which maps z onto a 28 by 28 matrix of floating point numbers in the range 0 to 1, one number for each pixel. Call this matrix P. Next, for each pixel, generate a Bernoulli random variable, i.e. a binomial with n equals 1, using the p for that pixel, and that is our random image. All the cleverness here is in the neural network and how it computes the p matrix. The probability bit that we've tacked on is fairly trivial. Okay, now let's set it up for training using an autoencoder. There are three things to specify in an autoencoder. First, the decoder, which we've already described. This is the bit that takes the latent variable z and turns it into an image. Next, the encoder. This takes an image, little x, and uses it to produce a sampling distribution z tilde. Third, we need to write our sampling distribution as a function of the output of the encoder and some other noise random variable. Here I'm going to choose to let z tilde equal mu plus sigma times f, where mu and sigma are computed by the encoder, and f is a collection of standard normals. There's no correct encoder, it's just modeler's choice again. Now, the autoencoder training objective is this big scary expression here. We have to train the F and G neural networks to maximize it. Let's look at it piece by piece. First, the likelihood piece. This is the probability model we proposed. We said we'd generate a P matrix, 28 by 28, and then we'll pick each pixel randomly, either 0 or 1, depending on P. So it's easy to write down the log likelihood of an image given P. It's just the sum of the log likelihoods of Bernoulli random variables, one item in the sum for each pixel in the image. And here's where I'll put it in the code. I'll define a class Bernoulli image generator, I'll let it store the parameters of the neural network f, and I'll define a log likelihood function which computes the log likelihood of an image x given the latent variable z. Okay, next term, the KL divergence term. Here's the definition of KL divergence. The KL divergence from a distribution z to another distribution z tilde is the expected value of the log of the likelihood ratio where the expectation is taken over the first distribution z tilde. In our case, we've already said at the top what the distribution of z tilde is. It's normal with mean mu and variance sigma squared. And the question told us what distribution to use for z. So we just plug all those things into the definition of KL divergence. Then there's a whole load of simplification. And then we just work out this rather simple expectation. It's based on means and variances of a normal random variable, so it's very straightforward. Actually, what I wrote out here is just for a single normal random variable, but we're using d of them in our latent space. And if we had written out the log likelihoods properly for d independent normal random variables, we'd end up needing to take the sum of this expression over all d dimensions. Now, here's the code behind the encoder part of the autoencoder. I'll define a class called Gaussian encoder. I'll let it store the parameters of the neural network G, and the job of G is to take an input image X and compute mu and sigma parameters. The way I've set it up here, mu and sigma are both d-dimensional vectors. And here's the line where I implement the KL divergence term. It's just a simple algebraic expression based on mu and sigma. Okay, so now let's put it all together. We want to maximize this quantity here, and it's the job of the function log-like subscript LB to compute that value for a single image X. We've already figured out the KL term. The only other bit is the expectation. We can do it with Monte Carlo. Here I'm using just a single Monte Carlo sample from F. I'll say call my sample epsilon. This gives me a sample value of z tilde, namely mu plus sigma times epsilon. And then I just evaluate the log likelihood of the data point at that value of z tilde. We've already implemented this log likelihood function inside the Bernoulli image generator class. And here is code for actually doing the optimization. It's just the usual PyTorch optimization stuff, nothing different. We iterate through the dataset, compute the quantity log-like sub LB on each image, and then ask PyTorch to maximize. The only slight thing worth modifying in the code I showed earlier is that it's more efficient to run on batches of data, and that's what PyTorch encourages. So in the actual code snippet you'll see online, I've modified both the generator and the encoder classes to work on batches rather than single data points. There is a lot to this code, and we haven't even got on to understand why it is that this is the function that we should be optimizing. But before doing the maths, I want to say a little bit about how to think about the terms in this equation and to get a feel for where they come from. Here's the equation again, but bigger. Let's think about the likelihood term first. And let's think about the data points and the latent variables. The autoencoder has two neural networks, the encoder network G that maps from the space of images to the space of latent variables, and the decoder network F that maps from latent variables back to images. If I take a single image X and I ask what latent value Z might have produced X, there'll be some part of the latent space that maps onto X. Or, strictly speaking, since X is a random variable, what I should say is there's some part of the latent space that yields high likelihood for this particular image X. Now, if I take the image X and ask what's the distribution of Z tilde that this image gets encoded onto, that'll also pick out some region. And the only way to get a high score from this likelihood term is if the two regions overlap. The encoder maps X onto some region of Z tilde values, and those Z tilde values need to generate X. If that's not the case, then the log likelihood term will be low. In other words, the log likelihood term is there to encourage the encoder and the decoder to be aligned with each other. We're not forcing it to happen, we're just encouraging the training to find parameters where it does happen. Next, let's think a bit more about the role of randomness in the Z-tilde distribution. Why do we even want the encoder to produce a random value? Wouldn't it be simpler if it just produced a deterministic value? Here's one way to think about it. Let's suppose there's some region of the latent space that tends to produce a given image X. And let's imagine that the decoder function f is horrible and discontinuous, and there are some nearby latent variables which map to a completely different part of the image space. Then, if I take X and encode it, even if the encoder puts it on exactly the right spot, on average, the randomness in Z-tilde might make it stray away, and then the discontinuous decoder might map it to a completely different part of the image space. In other words, if the decoder function is discontinuous, then it will score badly on the log likelihood term because of the noisiness of Z-tilde. In other words, this randomness encourages smooth decoders. That's what makes the latent representation meaningful. You can just tweak one of the dimensions of Z a little bit, and it will make a small tweak to your output image X. Finally, let's think about this KL term. Think about the spread of data points in the dataset. Obviously, it doesn't cover the entire set of all possible images. Most images are just static noise, and only a tiny fraction of images actually look like MNIST digits. Let's imagine that the decoder maps these images to just a few weird corners of the latent space. Maybe it puts all the 0 digits in the top left, all the 1 digits in the bottom left, and so on. This would be no use at all when it comes to using the F network as a generative model. If we just picked a random Z, remember that the Z distribution is specified as part of the generator, chances are it will map to somewhere that has nothing to do with the dataset. I don't want that. I want this to be a good generator. In other words, I want to be able to just run the generator on a random Z and get us a sensible looking image similar to what's in the dataset. That's basically what the KL term is there for. It penalizes Z-tilde distributions which are too much unlike the distribution that we want for Z. Okay, so I've talked through the rough intuition behind the terms in this objective function. It's great to have an intuition behind what the terms do, especially when it comes to debugging, but I don't trust intuitive explanations. Jesus taught in parables because he was teaching ineffable wisdom, but in machine learning we should stick to explaining what things are, not what they're like. There's no way we could possibly derive the autoencoder from this sort of hand-wavy explanation that I've just given. The autoencoder is a truly beautiful and precise balance, and its only real explanation is the mathematical derivation based on probability. That's what we'll look at in the next video. If we want to tweak things, if we want to design an autoencoder with slightly different goals, that's where we had better start.